테슬라의 미래 비전은 마스터 플랜에 자세히 나와 있습니다. 현재까지 마스터 플랜은 파트 3까지 나와 있습니다. 2006년 발표된 테슬라 마스터 플랜 파트 1은 멋지고 빠른 전기차를 생산해서 그 수익으로 가격이 더 합리적인 전기차를 만들고, 그래서 돈을 더 벌게 되면 가격이 더 낮은 전기차를 만들면서 공해 배출이 없는 전기 생산 방법을 제공하는 것이라고 했습니다. 테슬라는 멋지고 빠른 전기 스포츠카 로드스터를 개발했고요. 로드스터를 팔아서 벌어들인 수입으로 가격이 더 합리적인 모델 S와 모델 X를 생산했습니다. 그리고 모델 S와 모델 X를 판매한 돈으로 가격이 더 저렴한 모델 Y와 모델 3를 생산했습니다. 그리고 테슬라 에너지 비즈니스를 위한 태양광 사업과 에너지 저장 장치 ESS 비즈니스를 시작했습니다. 테슬라 마스터 플랜 파트 1은 이렇게 해서 모두 이루어지게 되었죠. 10년 뒤인 2016년 테슬라는 마스터 플랜 파트 2를 발표했습니다. 파트 2는 친환경 에너지를 생산할 수 있는 솔라 루프 시스템과 이 에너지를 저장할 수 있는 ESS 배터리 저장 시스템을 만드는 것이었습니다. 현재 솔라 루프 시스템은 여러 가지 문제로 우선순위에서 다소 뒤처져 있지만 에너지 저장 장치 ESS 시스템은 메가팩이라는 효율적이고 효과적인 시스템으로 매년 폭발적인 성장을 하고 있습니다. 캘리포니아 레이스업 지역에 메가팩토리 확장을 하고 있고요. 중국 상하이에 추가로 메가팩토리 착공에 들어갈 예정입니다. 그리고 많은 전문가들은 2027년을 전후로 해서 테슬라 에너지 비즈니스 매출이 전기차 매출을 넘어설 것으로 전망하고 있습니다. 이렇게 되면 정말 테슬라는 전기차 기업이 아니라 종합 에너지 기업으로 탈바꿈하게 되는 셈입니다. 그런데 여기에서 한 발 더 나아가서 마스터 플랜 파트 1에서 가격이 합리적인 전기차를 생산하려고 했다면 파트 2에서는 제품 라인을 확장하겠다는 선언을 했는데요. 현재 본격적인 생산에 들어간 세미 트럭과 곧 고객에게 인도를 시작할 사이버트럭까지 테슬라 전기차 라인업이 확대되었습니다. 그리고 향후 기존 모델의 반값 전기차인 넥스트젠 모델 2까지 계획하고 있습니다. 정말 놀라운 발전입니다. 마스터 플랜 파트 2 세 번째는 사람보다 10배 더 안전한 자율주행 기술을 개발하는 것입니다. 앞서 여러 영상에서 설명드렸듯이 테슬라는 이제 베타 딱지를 뗀 FSD 버전 12 정식 버전을 출시하려고 준비하고 있습니다. 일론 머스크는 테슬라의 엣지 컴퓨팅으로 설명되는 각 차량의 자율주행 컴퓨터 하드웨어가 현재 생산하고 있는 도조 슈퍼컴퓨터로 본격적인 인공지능 자율주행 학습을 완성하고 나면 파트 2에서 계획했듯이 사람보다 10배 더 안전한 자율주행을 현실에서 선보이게 될 것으로 생각합니다. 그리고 자율주행 소프트웨어 FSD를 기반으로 해서 파트 2 네 번째 계획은 바로 자동차를 이용하지 않을 때 수익을 발생할 수 있도록 하는 로보택시 서비스를 출시하는 것입니다. 평소에는 자신의 이동수단으로 사용하지만 사용하지 않는 더 많은 시간에 수익을 창출할 수 있게 되는 것인데요. 바로 로보택시 플랫폼으로 확장하는 것입니다. 정말 기가 막힌 발상인데요. 그런데 정말 이러한 꿈이 현실에서 이루어지려고 하고 있습니다. 멀지 않은 시점에 말이죠. 그래서 2016년에 발표된 테슬라의 마스터 플랜 파트 2는 이제 곧 완성 시점을 앞두고 있다고 이야기할 수 있을 것 같습니다. 그리고 드디어 2023년 테슬라의 장대한 마스터 플랜 파트 3가 발표되었습니다. 규모가 정말 어마어마한 프로젝트인데요. 개별 기업이 아니라 세계 기업 혹은 세계 정부가 나서야 할 정도로 비전이 크고 원대한 프로젝트입니다. 마스터 플랜 파트 1이 저렴한 전기차 개발을 목표로 했다면 파트 2에서는 에너지 저장 장치와 솔라루프 그리고 자율주행 개발을 목표로 했습니다. 그리고 이번 파트 3에서는 테슬라가 종합 에너지 기업으로 도약하기 위한 발표라고 생각됩니다. 2050년까지 전 세계 에너지 소비의 100%를 지속 가능한 에너지로 대체하기 위해서는 태양광과 풍력 같은 재생 에너지를 활용해서 30테라와트의 친환경 에너지를 생산하는 것을 목표로 하고 있습니다. 그리고 이 에너지를 저장하기 위해서 240테라와트 시의 저장 장치가 필요한 것으로 분석했습니다. 이 계획을 위해서 테슬라는 약 10조 달러의 투자가 필요하고요. 친환경 에너지는 현재의 화석 에너지보다도 낭비되는 에너지가 적고 에너지 효율도 좋아서 현재 필요한 에너지의 절반 정도만 있어도 충분하기 때문에 2022년 세계 경제 생산량 GDP의 10%에 해당하는 10조 달러만 있어도 가능하다고 설명하고 있습니다. 그리고 현재 에너지 비효율성으로 인해서 70%가량이 버려지는 화석 에너지를 전기 에너지로 대체하는 것이 필요한데 2050년을 목표로 지속 가능한 에너지로의 전환을 하기 위해서 에너지 패러다임을 구체적으로 다음과 같이 변화시키려고 하고 있습니다. 35%의 태양광 발전, 21%의 전기차 전환, 22%의 히트펌프 전환과 17%의 산업용 수소 전환, 그리고 5%의 비행기와 배를 친환경 에너지로 전환하게 되면 화석 연료를 줄일 수 있다고 했습니다. 태양광 산업은 꾸준히 발전해서 10년간 연평균 33%라는 놀라운 성장률을 기록했는데요. 지난 10년 동안 태양광 발전 설치 비용 역시 60% 이상 줄어든 것으로 나타났습니다. 그 결과 대규모 발전소인 유틸리티 규모의 태양광 발전소에서 생산된 전기의 가격은 다른 전기 공급원보다 경쟁력이 있는 메가와트 시당 16달러에서 35달러 사이로 책정되고 있습니다. 테슬라는 이러한 현상에서 앞으로 태양광 발전이 지속 가능한 에너지 자원 중에 가장 핵심적인 자원이 될 것이라고 전망하고 있는 것입니다. 전기차 전환으로 넘어가 보면 2022년 전 세계 전기차 시장 규모는 2,055억 달러로 추정되고 있는데요. 앞으로 10년 후인 2032년이 되면 세계 전기차 시장 규모는 1조 7,168억 달러로 늘어날 것으로 전망하고 있습니다. 향후 10년 동안 연평균 성장률 CAGR이 무려 23.1%가 된다는 것인데요. 이러한 추세는 전기차 산업의 생태계가 폭발적으로 확장된다는 것을 의미하고 앞으로 30년이 지나면 완전한 전기차의 시대가 도래할 것으로 전망하고 있는 것입니다. 히트펌프 전환으로 넘어가 보면 건물 내의 난방 시스템을 히트펌프로 전환하게 되면 에너지 효율성이 기존의 3배 이상 높아진다고 합니다. 앞으로 지어질 건물들은 히트펌프로 전환해서 향상된 에너지 전달 기술을 적용할 것으로 전망하고 있습니다. 산업 분야에서는 산업용 수소를 활용해야 한다고 하는데요. 제철, 화학 및 정유와 같은 주요 산업들이 전통적인 화석 연료에서 벗어나서 수소를 주요 에너지 원천으로 선택하게 되면 고효율의 에너지 원인 동시에 지속 가능한 친환경 에너지 원이기 때문에 환경적으로 그리고 경제적으로 큰 이익을 얻게 된다고 합니다. 마지막으로 비행기와 배 역시 전기 에너지로 전환하게 되면 많은 양의 온실가스를 줄이고 에너지 효율도 높일 수 있어서 지속 가능한 에너지 전환을 촉진시킬 수 있다고 설명했습니다. 이러한 지속 가능한 에너지 전환을 촉진하도록 이끄는 것이 바로 테슬라의 마스터 플랜 파트 3의 핵심 비전이며 전기차 기업에서 종합 에너지 기업 그리고 자율주행으로 대표되는 인공지능 소프트웨어 기업으로 탈바꿈하는 구체적인 로드맵을 제시한 것입니다.
All right, Master Plan Part 3. The story, and I think this holds together quite well, and we'll be actually publishing a detailed white paper with all of our assumptions and calculations, is that there is a clear path to a fully sustainable Earth with abundance. In fact, you could support a civilization much bigger than Earth, than much more than the 8 billion humans, could actually be supported sustainably on Earth. And I'm just often shocked and surprised by how few people realize this. So we're going to walk through the calculations for how to create a sustainable energy civilization.
And to set the stage, today our energy economy, let's be honest, it's dirty and it's wasteful. over 80% of global energy, primary energy, comes from fossil fuels, and only 1/3 of that global energy actually ends up delivering useful work or heat. This is the problem statement, but we're here to talk about the solution.
So, if you have a gasoline car, you're converting less than a third, often maybe only 25% of the energy in the gasoline is converted into motion. The rest is turned into waste heat. That doesn't do any good at all. And there's a lot of energy required even to get the oil out of the ground, to refine the oil, and to transport the gasoline to the gas station. So when you look at all that, for a typical gasoline car is actually going to be using less than 20%, fully considered, of the energy from the oil actually goes into motion. So this is when we see people doing calculations for what does it take to create a sustainable energy Earth, they assume that the same energy amount is required for an electrified civilization versus a combustion civilization. This is not true, because most of the energy of combustion is waste heat.
But the nice thing about electrified economy, through end-use efficiency and through efficiency along every step of the way, actually the total energy use halves. So this is one of the most enabling aspects of electrifying everything, is that the sustainable energy economy is that much easier to accomplish. It's actually half the problem statement of the fossil fuel economy.
Yeah, and we're being conservative here, so it could be better than half, but we're trying to have assumptions that are reasonable, not overly optimistic, in fact, slightly pessimistic.
So how the master plan works, you want to talk about?
The thing that is needed at very large scale that is not currently present is a vast amount of battery energy storage. Our rough calculations are that this is about 240 terawatt hours, or 240,000 gigawatt hours. So if you've got solar or wind, you've got to store the energy when the wind is not blowing, the sun is not shining. And so we're assuming sort of an 8-to-1 ratio of stored energy to power, so 30 terawatt hours of power, 30 terawatts of power. Our capital expenditure calculation for manufacturing investment is more like 6 trillion, but we made it higher to make it 10 trillion.
And this is across mining, refining, battery factories, recycling, vehicle factories, all the things that we're going to talk about needing to invest in to build the sustainable energy economy.
Yeah. Now, if you look at the total world economy, it's just under 100 trillion. So if this was spread out, say, over 10 years, it would be 1% of the global economy. Over 20 years, it would be 0.5% of the global economy. So this is, not a big number relative to the global economy. As Drew mentioned, you need about half as much energy with an electric economy versus a combustion economy. And in terms of wind and solar, how much land would be used? It's less than 0.2% of the land area of Earth. The electrified economy will require less mining than the current economy does.
Yes.
Less, not more. Okay.
So this is the plan, and now we'll get into a little bit more of the details of the plan. Basically, 5 areas of work. First, renewable power the existing grid. Second, switch to electric vehicles. Third, switch homes, businesses, and industry heating to heat pumps. Fourth, high-temp heat delivery and storage for high-temp industrial and chemical processes, and a little bit of green hydrogen in there for chemical processes that need hydrogen. And finally, sustainably fuel planes and boats. These are the 5 areas, and we're going to go into detail on all of them.
Yeah, I mean, my personal opinion is that as we improve the energy density of batteries, you'll see all transportation go fully electric, with the exception of rockets.
So first, repowering the existing grid with renewables. And this is going to be a consistent theme. You'll see our estimates for the number of terawatt hours, terawatts, and trillions of investment at the bottom of the page. This is already actively occurring in front of us. 60% of the generation added to the US grid was solar in 2022. And actually, on a year-on-year basis, solar deployment is growing 50% year-on-year as of 2022. So this is a serious upswing. And if we continue this trend, This is going to be behind us before we even know it.
Yeah.
Second, switching to electric vehicles. Again, 21% reduction in fossil fuel use by doing this alone. Obviously, Tesla is heavily engaged in this activity, along with many others. Overall, EV production grew 59% year on year in 2022. And what does this fleet look like? You know, just rough view from our perspective. Of course, we could be wrong, but you know, you can see the sort of breakdown of the fleet by millions of vehicles. You know, our goal is to do 20 million electric vehicles a year. And one of the reasons why EVs are so enabling is this end-use efficiency point. Tesla Model 3, it's 4 times more efficient from the well to wheel than a Toyota Corolla. And that's all about the efficiency of getting the electricity into the car in a sustainable energy economy, and then how efficient the car is in transferring that stored energy to motion on the road. Next, switching to heat pumps in homes, businesses, and industry. You know, right now heat pumps meet 10% of building heating needs. Install rates growing 10% year on year. It really needs to accelerate. Heat pumps can serve, you know, heat applications up to 200 C in businesses and industry. And from an investment perspective, as you can see on this page, this is actually the lowest hanging fruit in terms of displacing fossil fuels. You know, they're all over this factory, they're in your house, and all this really is about bringing them to displace all the fossil fuel heating in all of the homes, business, in the industry that we can. And from an end-use efficiency perspective, there's a three times reduction in the total energy required to heat these buildings. Next, a little bit more detail on electrifying high-temp sort of industrial chemical processes. So over 50% of industrial heat is greater than 400 C. You know, cement, steel, fertilizers, chemicals, plastics, metals refining all need like 1500 C, so we need a solution here. Ultimately, it's purpose-built equipment that enables electrification. You know, carbon graphite is stable up to 2800 C. There's other options in the 1500 C range, like silicon carbide, other materials. And then on the hydrogen side, we also need green hydrogen to decarbonize metals and chemical refining processes. This is things like ammonia, making steel. You know, there's roughly 120 million tons of hydrogen sourced from fossil fuel today to do these things. And hydrogen can also directly replace coal, which is currently used in a ton of steel production, through a process called directly reducing iron. You can replace blast furnaces with a hydrogen-reducing, direct reduced iron furnace. And this is the way to eliminate fossil fuels from these aspects of the economy. And lastly, a small part of the pie, but a necessary part of the pie, is sustainably fueling planes and boats. Shipping accounts for 3% of global CO2. It's ripe for electrification. Even with lithium iron phosphate, long-haul ships can be fully battery-powered. So that's a great opportunity to electrify. Energy density is a little bit harder for planes, but short haul is doable today. With some improvements, we'll get long haul underway. But even in the meantime, we can leverage sustainable aviation fuels produced and stored using excess renewable electricity. There's a lot of work going on in this space.
Yeah, I mean, to really get long-range aircraft and long-range shipping to use lithium-ion, you need to redesign the ship and not just...
or the plane.
And the plane. To take advantage of the fact that it is a new source of energy. It's a different architecture. Make it mass efficient and optimized for batteries. The same, if that's done with aircraft, I think you can get long-range aircraft at around with cells at around 450 watt-hours per kilogram, which you can buy it right now. Actually, they're expensive, but I think that price will come down.
So when we stack up all of these efforts, we end up with the numbers we shared at the beginning of the presentation: 30 terawatts, 240 terawatt hours, $10 trillion. And you may be saying, like, I need some context. Is this feasible? Spoiler alert, it's entirely feasible. Just looking at it from a growth rate perspective, how much do we need to grow the deployment of these technologies? We're talking about only a 3x growth rate in solar and wind deployment. When we look at the electric vehicles, they have to grow 11x. Well, they grew 60% year on year last year. That growth rate is also going to close pretty darn. That gap is going to close pretty quickly as well. And lastly, storage. You know, Tesla's energy storage business has grown at 65% CAGR since 2016. The global, energy storage business is accelerating pace as well. I mean, all these gaps are going to close, especially as this momentum of the transition to sustainable energy accelerates. And of course, our goal on this page is 20 million EVs per year and 1 terawatt hour of stationary storage per year, basically as soon as we can. And then, what about this investment? How do I have a reference point on this investment? Elon mentioned it's 10% of 1 year's world GDP. Another way of thinking about it is how does it compare to what we're investing, like what we invested last year in the fossil fuel infrastructure? And it's 60% of that investment. So actually, building this sustainable energy economy is less than extending the fossil fuel economy from a year-over-year investment basis. So very doable.
Yeah.
And what about on the mineral extraction side? So this is a cartoon that sort of gives you a sense for all the ore and the extracted minerals that are coming out of the earth every year. It's about 68 gigatons. So each truck is a gigaton. What does this look like when we're in a sustainable energy economy? Looks like that. The fossil fuel extraction disappears. We replace it with the materials required to fulfill the sustainable energy economy. It actually reduces. And then when we calculate it on a sort of element by element basis, the resources are there to support the transition. This is cumulative demand to move in the sustainable energy economy direction until 2050 relative to USGS resources today. We're not breaking the resource bank for any of these materials. And then when we look at what really happens as we move forward, history teaches the more we look, the more we find. What people think happens is, oh, there's this many resources, next year there's going to be less because we're going to extract them. What actually happens is, as we extract resources, we find more. And you can see on the right what has actually occurred with the key materials to the sustainable energy economy. Since 2000, as the sustainable energy economy has been growing, and Tesla's been growing, and all the industries around us have been growing, the actual resource availability has increased, not decreased. Yeah, and ultimately, this resource extraction, we go through this effort, we build these batteries, and then we recycle these batteries. So ultimately, we're doing this to build this sustainable energy economy, but the maintenance amount of ore that we require is really an order of magnitude or more, less, because of recycling. So in the end, a sustainable energy economy is within our reach, and we should accelerate it.
Yeah, I mean, so this is really the main message of today. And I really wanted today to be not just about Tesla investors who own stock, but really anyone who is an investor in Earth. And what we're trying to convey is a message of hope and optimism. And optimism that is based on actual physics and real calculations, it's not wishful thinking. Earth can and will move to a sustainable energy economy, and will do so in your lifetime. Thank you.
Yes. Thank you. And I just want to welcome up Lars and Franz to the stage.
So when you think about what I'm trying to say, I really want to hammer this home. When you have a car that's about 5 meters long, and you have people working around it, like we did in Model 3, and we change that to this process where we take different parts of the car, and we can do more at the same time, like we did with the Model Y structural battery pack. What you see here is us doing that on the front part of the vehicle, or the rear part of the vehicle. That means we can get more people working on the car, or robots, working on it at the same time. That means we have better operator density, less time doing nothing. We get 44% more operator density, which means more work, less time walking back to the station, 30% improvement in space-time efficiency. And because we're not building it in and out of the car with those slow movements of those robots I showed you from production hell, when we go to automate it, it's going to be a lot easier. In the end, that will probably look something like this, where we balance parallel and series manufacturing in a way where we only do things that are necessary, with a much shorter final line, blocking a lot less of the entire rest of the factory, so we can optimize material flow using the best practices. And what that means, it's going to look something like this, where we build all the sides of the cars independently, we only paint what we need to, and then we assemble the parts of the car once and only once. We put them where they need to go. The interior is attached from a bottom-up or a top-down strategy, so there's more access for those robots and people. We aren't moving heavy objects around and doing nothing to it. And it means we're doing more work on the car more of the time. And then when we take all of these tested sub-assemblies and we put them together, we finally assemble the car only one time, putting the sides on with all of their parts to a front and rear that was already assembled, carrying the floor in with the seats, and finally boxing it out with the doors one time, just like Cybertruck. So in the end, you get the same car, but it's not going to be a Model Y.
Yeah, this is not. Yeah. This is a Model Y for illustration, not the next-gen vehicle.
In the end, what does that mean? To increase the scale and adoption of electric vehicles on the orders of magnitude that we just showed you, we have to make constraints part of the solution. It leads us to greater than 40% reduction in footprint, which means we can build factories faster, with less capex and more output per unit. We'll reduce costs as much as 50%. This is the 2-for-1 concept you hear me and Elon talking about on earnings calls.
Yeah, so I think our track record proves that we can deliver the best cars, and we deliver the best cars in spite of, because of these constraints. And I'd love to really show you what I mean and unveil the next-gen car. But you're going to have to trust me on that until a later date.
Thank you, Franz. My name is Colin Campbell, and I have the real privilege of leading powertrain engineering here at Tesla. And the powertrain factory, which is behind me today, is 75% smaller and 65% cheaper than the one that we originally built. In our next powertrain, so those silicon carbide transistors that I mentioned that are key component but expensive, we figured out a way to use 75% less without compromising the performance or the efficiency of the car. And of course, we know that battery cell supply is one of the constraints on the scalability of EVs right now. Our new powertrain is compatible with any battery chemistry. And that will give us great flexibility in battery sourcing. If we want to make EVs more accessible to people, they have to be cheaper. We've reduced the drive unit cost to about $1,000, and we don't think any other automaker is even close to that number. We have designed our next drive unit, which uses a permanent magnet motor, to not use any rare earth materials at all. And this achievement, like all of the achievements that I mentioned today, it's only possible because of the incredible people on our powertrain teams. They are absolutely committed to the cause of sustainable energy, and that is why we can do what no other company can do.
Good afternoon, everybody, and welcome to Texas. For Cybertruck, we are now designing 85% of the controllers in the car. For the next-gen platform, we're going to finish the job and be designing 100% of the controllers to give us full control of the design and the supply chain at the component level.
Thanks, David and Pete. Hey, everyone. My name is Ashok Kelliswamy. I work on autopilot and self-driving. Like I mentioned earlier, the solution to scalable FSD is getting the AI architecture, the data, and the compute just right. And we have assembled a world-class team to execute on this. We're pushing the frontier on these 3 items, and as we improve the safety, the reliability, and the comfort of our system, we can then unlock driverless operations, which then makes the car be used way more than what it's used right now.